but I think I understood what I did. But my understanding is not gonna be the same as yours, but I think I get it.
Okay. All right.
Yeah.
Give us some easy stuff though.
That's all right. We're gonna review it again. If you still don't get it after today, come for tutor.
Study hall.
That's what I'm talking about.
See you after class. Yes. That's
I'll see you
so we know that what's the law of electrostatics? Up here.
Opposites attract.
The opposites attract,
like
and
charges
symbols
should repel.
repel.
So the question that I asked in class was if the protons are all positive, according to that law, they should be repelling each other, right?
Yeah.
But how come they're all together in the nucleus? Because of the binding energy.
Of what?
Hold on, I'm getting there. So, when the protons are all separated, imagine they're all separated, doing their own thing, hanging out, whatever. But in order for them to come together, they need to sacrifice something,
Mass.
and that's gonna be their mass.
That's all I remember.
So once they sacrifice that mass, it's converted to an energy. That is called a nuclear binding energy.
Ma'am,
Yes.
mass as the weight or mass as the what we learn as KVP and mass?
Mass as their
Weight.
weight. Yes.
Thank you.
Not KVP and mass. So, what is the law about energy? It is neither
Destroyed or created?
destroyed or created. It has to be transferred from one form to another. So in this case, the energy that we get it from the mass that's lost. They have to make a sacrifice in order to come together. So basically, the force of the repelling is weaker than the nuclear binding energy. It has a stronger force that keeps them together. So for example, imagine if you had two pieces of magnets, and usually if you hold them together, they should kind of move your hands with it because they're repelling each other, right? But imagine we had really, really, really powerful glue, Gorilla Glue or whatever. So if we held them together, we could probably stick it together, right? So that's kind of like a nuclear binding energy. So that has a stronger force than the force that it naturally has to repel each other. Make sense so far? Just know this for the test. The nuclear binding energy has a stronger force than the force of repulsion between the protons.
And the nuclear binding energy comes from the giving up of the mass of the protons to converting into the
Yes.
The question where it says, if the nucleus is made of protons and neutrons, that one is because they're positive?
Why don't the protons repel each other? Because they're both positive, right?
Yeah.
So that's why they repel each other.
No. Why don't they repel each other?
Because of the
Yes.
because of the nuclear binding energy be
Stronger than the force of
the
repulsion.
repulsion.
Does that binding energy hold the protons?
Yes. Right? So I just went over this. Where do we get the nuclear binding energy?
Giving up of the mass.
Energy equals mass times the speed of light squared. And according to the law of conservation of energy, we know that energy can neither be created nor destroyed. So like, the protons can't just create it out of nothing, right? It has to come from something. And it comes from the sacrifice that the neutron or the protons make of their mass. So the mass that is sacrificed is converted into the nuclear binding energy.
So the nuclear binding energy formula is energy.
No, that's just Einstein's equation for energy. That's not.
Ma'am, that doesn't work for all energies. It should. I don't know. The binding binding energy is energy, so it should be matched.
It's working for this one, so just worry about this.
So this is the,
Energy for work.
Yes. So if you look over here, if we separated all of the nucleons, and for example, if they had a mass of 2 each, how much would the total mass would be?
MC squared.
So we have
4,
7 here,
16,
right?
Okay,
7
plus
times 2 is 14. But when they come together in the nucleus, they give up some of that mass. So from 14, they probably went down to 7.
Do you want us to remember that equation?
Yes. What is equals mc squared stand for? Energy equals mass times speed of light squared.
Speed of light is 10.3.
What's the number for speed of light again?
2 point something.
3
times
times 10 to the
3 point.
3
You serious?
Speed of
Now,
light.
I myself.
What's the speed of light?
It's 3 point.
I know it's 3 point something.
3.08? Oh,
Speed of light.
J?
The speed of light is 670,616,629 miles per
no,
hour.
not
No, I
Mr.
think it's like
Fong's.
3.7.
Not Mr. Fong's. What?
My brain.
10 to the power of 8, right? 2.7
You said
to
Mr.
10
Funk,
to the
right?
power
Yeah,
of
you know
8.
he broke his down. like
Yeah,
that.
he did,
But-
but you know he would have done it
It's
further
2.9.
and
It's
converted to
2.7
kilometers
to
an
the power
hour.
of 8, if I'm-
That's Mr. Fun.
my
Yeah.
memory is-
Metric system.
3 times 10 to the power of 8.
Yeah, I said-
Yeah, the
I said
2.7 if you
Yeah,
can
that's what I
round
said.
it.
3
The
times 10
rounding
to
it
the
to
power.
3, ma'am. It's 2.7 if you can.
It's 2.9.
Yeah,
2.9?
so just remember, hello, 3 times 10 to the power of 8.
No, but I might as well remember what we know from the.
Now, if you want to get it right on her test, she
So
said
what did
put
Mr.
that.
Fong say?
All them numbers.
3 times 10 to the power of 8?
Yes. And then he put it
Yeah,
in.
I don't know where you got that from.
Is it 2.9?
No.
Just
Remember,
remember,
it's
3 times
2.9872645.
10 to the power of 8.
For her test, like she said, man.
You should put 2.9 in the
It's
test.
2.98.
I will, just to confuse y'all.
Yeah.
So another way to think about the nuclear binding energy is that it is also the energy required to break the nucleus apart. So what that means is if somebody wanted to break the nucleus apart, just for fun, they would have to get the energy equal to or greater than the nuclear binding energy.
Ma'am, I have a question.
Yes.
Each atom has some binding energy, or the nuclear has a particular binding. This is particular binding. Now, when we said that because of the mass,
The
it is-
nucleus has a binding energy.
So each atom
it's not
has
with the atom.
each atom has a binding energy.
So each
Because-
atom has protons and neutrons and a nucleus. So each atom does have. We'll get into different binding
Does
energies.
it add up to this amount, or the each one has the same binding energy that you're talking about?
Different because there's different number of protons and neutrons, right?
They're not all the same.
Yes.
But
So
we
My
have
bad, just
elements.
not-
We have certain elements that are the same. Those are predictable. Those are the same.
I don't think she
So like if you had 4 tungsten atoms, they're
My
all going to
question,
be the same.
ma'am, my question was the binding energy is the energy of each atom, or is it the accumulation of atom gives that particular energy?
so the binding energy is basically the energy that the nucleus has.
For
So
that.
every different atom will not have the same amount because they
It'll be
all have
different-
different protons and
And
neutrons.
neutrons.
But each atom does have its own binding energy.
Thanks, ma'am.
So what do we measure nuclear binding energy with? MeV, mega electron volts. By the way, does this definition ring a bell? Where have we heard
Which
the interactions that produce X-rays?
or what's it called?
Characteristic and Bunsen, which we'll get into in just a second.
It might be the only thing.
Ask me after the semester.
What is the,
Pull up my hair.
what's the notation for
Eighth
mega?
grade, I feel like
The scientific notation? Is it 10 to the ninth or is it, I think it's 10 to the seventh?
I'm not sure. I'll have to look it up.
Mega is 1,000.
No, kilo
Ten.
is 1,000. Mega,
100,000.
I don't think there is a number, but if there is, I will let you know.
but we don't need to know it, right?
You don't need to know it for the test. Alright, so we just went over nuclear binding energy. That's the binding energy of the nucleus. Now we're gonna talk about the binding energy of the electrons. So, what are the electrons doing, by the way? Just
Rotate.
standing still, or
They're
they're
rotating.
orbiting
Yes.
around the
Orbiting.
nucleus?
Revolving.
Right, and we already know that the electrons have a negative charge, and the nucleus has a positive charge because of the protons. That's why the electrons are very attracted to the nucleus, and they stay spinning around the nucleus. Instead of just floating around and doing its own thing, they're always found orbiting around the nucleus, right? So that attraction leads to the electron binding energy. And that is what keeps the electrons orbiting around the nucleus. The proton? No. The electrons
getting this.
are orbiting around
No,
the
person.
nucleus
No.
because of the electron
juicy fruit or
binding.
something like that.
Sounds good.
So the electron bonding energy is created because of the attraction between the electrons and the protons in the nucleus.
Yes.
Gotcha.
Due to electrostatics.
Don't confuse them.
That's
So
what
if
I
I
said,
ask you a
right?
question on the test,
It says it
what
right there.
keeps the electrons in orbit?
The nuclear
Electron
bonding.
binding energy.
Electron,
you-
yes, what you said.
What keeps the electron in orbit around the nucleus? The electron binding energy.
Would you,
What's two different things?
The bind because the way that the definition is
and electron binding energy are different.
Mhm.
Right.
So what's the nuclear binding energy?
Nucleus,
what's the
the nucleus binding.
That's what's keeping the
The
protons
energy that
Protons.
keeps
The
the
protons and the
protons,
nucleus.
neutrons together in the nucleus. The electron binding energy keeps the electrons in orbit. They're constantly spinning, right? Do they ever stop? No, because they have what's called the electron binding energy.
so,
Did it because I heard Nancy say the proton and the nucleus, the neutron, then it, what keeps the proton, what in the nucleus you said?
What is the nuclear binding energy that we went over?
Nuclear binding energy is protons and neutrons, only the protons.
No, it includes everything in the nucleus. Everything in the nucleus sticks together because of that energy. And then the electrons are always kept in orbit because of
electron binding.
Yep. That's it, simple.
Is it?
It is, unless you just want to confuse yourself.
Charo.
It's simple. I was just playing.
Miss Bonilla.
Yes.
So, the distance from like the nucleus to the shell is maintained by electrostatics, but the electron binding energy is what keeps it like spinning and in orbit.
In orbit,
So
that's
that's the
correct.
difference between the two.
Yes.
So those are two different test questions, right?
But she said you
Possibly.
were-
But don't worry about electrostatics right now.
Okay.
Or at least not yet. So, now we're gonna get into the different shells of the electrons. So we know that the first shell is called
K shell.
K, and then L, N, and so on and so forth. So, the electron shell that is closest to the nucleus, which is K shell, has the strongest binding energy. Okay? So if I asked you, compared to the K shell or the M shell, which one has the stronger electron binding energy?
K
The
shell.
K shell. So this is based on Coulomb's law. The force of attraction is inversely proportional to the square of the distance. Basically, in simple terms, the closer the electrons are to the nucleus, meaning their distance is the shortest, the stronger the electron binding energy.
Does that mean the K shell moves the fastest?
No, I believe they all have the same velocities. They just have different binding energies.
See, you can see the movements.
Yeah, but that's probably not like the scale. Because I was thinking if they, the further out they are, the more distance they have to travel, and the more electrons are in there.
Maybe they
bouncing off
increase the
each other.
speed.
Right. That's what I was thinking. But what the heck does this mean?
What the heck does it mean? That's what it means.
So is our quiz today or?
What do you mean by the last point, man?
So the electrons in the outer shell don't see as much of the positive charge from the nucleus because they're very far away from the nucleus, right?
They travel in opposite directions like that though?
What?
That's just a illustration. That's not meant to ask you which direction you travel.
So, ma'am, your point, last point, why is it there? How does it affect them?
What do you mean?
Electron in the outer shell don't see as much of the positive charge. So how does it affect them? They lose.
Their
They're easy
binding
to-
energies
They are low.
are weaker.
So weaker. But that's what.
Basically, the force of attraction is weaker
Mm.
the further out they are. Right? So, before I said with nuclear binding energy, that's the energy that's required to break the nucleus. So similarly with the electron binding energy, that is the energy required to remove a specific electron from the atom. That should be familiar to us, right?
Yes.
So, if a particle strikes the electron with the energy equal to or greater than the binding energy that it has, it can remove that electron from the atom.
Yes, ma'am.
But if a particle has a weaker energy than the binding energy, it won't be able to remove the electron. So where have we heard of this before? Characteristic and Bremsstraff law. Classical, that's scatter, right? Yeah, we're talking about, for X-ray production. And then for the electron binding energy, the units that we use are EV, electron volts. So MeV is for nuclear, and then EV is for electron. So, electron binding energy, why it's important to X-ray production, is that if a particle strikes the electron with an energy that's equal to or greater than the electron binding energy, it can remove that electron from the orbit. Not a K. I'll tell you in just a second. So, characteristic X-ray photon, right? So we have an incident electron coming from our, where our X-rays produced?
From the filament.
From the filament. It comes in with an energy that's really, really great, and it's able to knock this electron out of the K shell.
Which is
Right.
69.
Nice.
So now this shell is empty. So then the electrons in the second level jump in to fill that space. So in that process, that's how we produce characteristics. And then with bremstalung, we have the electron coming in, it's trying to get close to the nucleus, but then it breaks and changes direction. So in that process, that electron loses a whole bunch of its energy. And then remember we said energy is neither created nor destroyed, it has to be transferred. So that energy is transferred in the form of a bremsstrahlung X-ray photon. Okay? Alright. Yes.
I have a question.
Yes.
So during characteristics, when it ejects the K shell, there's no electron in the K shell?
It only goes from 2 to 1. So then remember the electrons are attracted to the nucleus, so they're always trying to jump in. So the electrons from the outer shell are going to jump in and fill that space.
So it's like a cascade. So what happens to the outermost shell?
Outermost shell must always have 8 at all times. But don't worry about that for this.
Oh.
Just know how is a characteristic X-ray produced.
That's why ionizing radiation is dangerous.
I did this with you. So like if one came in, okay, an incident electron knocked out the one from the K. One of the ones from like
How many of them are
P
there?
can move forward, or is that something different? You know, like when they jump from the shell. Yeah, like that, or it has to come from L and then the one from M.
Yeah, so the one from L is gonna jump in, then one from M is gonna jump into L,
Okay,
like
so
that.
they don't jump.
Yeah, they don't jump from all the way from
But they
M.
can jump.
Yeah, they can't.
No, they
There's-
can. They can.
They can?
Yeah, they
To
can.
K?
It doesn't have to go in
He said,
order.
but it's not common.
Yeah, it's
Oh,
not as
they
common,
can.
but they can.
Okay.
But that's why it usually goes like that, cause that makes that character.
That's what makes the cascade.
Yeah. If it goes from like, the one from the K moves out, so the L moves up, and then it goes from L and then M.
But if you're having a jump from P to K versus L to K, it'll have the
Stronger
photon
energy.
will have a more, stronger energy
Gotcha, okay.
compared to.
Yes,
L to K.
so, that's what it says here at the bottom. The energy of the X-ray photon that's produced depends on the difference in electron binding energies. So basically what Monty just said, if the difference between the binding energy of the shells are greater, then the X-rays that's produced is gonna be stronger. So from L to K, it wouldn't be as strong as, for example, M to K or something like that. Melanie has given up.
No, cause we already went over this.
That's why it's not common.
Ya lo sabes.
We're saying it can.
Oh, yeah.
So if I ask you, what are the 2 key types of atomic interactions responsible for X-ray production? It will be
I don't know nothing else, I know that.
Alright, so now we're gonna move on to talking about the different energy shell, or energy levels, or electron shells. So, electrons have set energy levels. These are the rules, 4 rules that you have to remember. Only a certain number of electrons can be at a single energy level at any one time. For example, K
2.
will have 2, because we're gonna use that formula 2n squared, which we'll go over in just a second. And these energy levels are called electron shells or electron orbitals. And last one, keep in mind that while drawn as a circle, in reality, they don't exist in just a circle. They're probably going to look something like this in 3D. Yes?
This isn't really important, but what atom is that, or element? Oh, I couldn't read that, I'm sorry.
I don't know what's in W.
Yeah, I wasn't sure if that's right.
That's an image that Mr. Fong had on there, so ask him.
The W stands for Wilson.
Yes.
Oh, no, W is tungsten.
Really?
Mm-hmm.
Oh, sorry.
This is
You said no these 4?
That's a Bohr
Yes.
model. What'd you say?
N equals tungsten.
You say M equals tungsten.
or stands for?
Yeah, it's 74. That's on.
Like that.
Yes.
One for men.
So what?
But after you put the names,
Mm.
depends on characteristics.
Oh,
But not
okay.
This is
identity.
This is the one that gets ejected. So valence electron gets ejected. Another calcium or whatever that's in the bone. Another bone.
I'm not fast enough for that.
If I'm typing, I'm turning it
Whatever
on.
comes in, then now they're
And
filled.
also, I have to write it down.
Now this has a missing space too. In the middle. So that's how cancers like really get going. Because it keeps happening over and over and over again.
Like they're not flat, they're like this.
When we use
So they're not
radiation
moving
to
in
kill
perfect
cancer,
little circles all the time. They can be anywhere around
Really
it.
like that.
obliterating it.
But within that, they're in their shell.
Correct.
Putting it up there in a specific spot to erase like all of the electrons.
Thank you.
So those protons just disperse.
Yeah,
Thank you.
thank you.
Thank you, ma'am.
But then you get proton therapy.
All right, so
Bless you.
electron shells are labeled starting with K, which is the most inner shell, right? And then we move outwards, L, M, N, O, P, whatever. So, important thing to understand is that shells do not necessarily fill all the way before the next one fills. So just because a K usually has 2 does not mean that it must have 2 all the time. So they have a maximum number that they can have, but there is no minimum requirement. It probably will have one at least.
Stronger though, right?
Yes. And then the second shell, which is L, how many electrons will it have maximum? 8, 2n squared, right? But it can have 7 or 6, but it can never have more than 8. Does that make sense? Anyone confused?
You said 2n squared.
Mm-hmm. Say that again?
I thought 2 times 2 is 4.
2n squared. So what is n? The level of the
Shell.
shell. So if I'm
So it'd be
asking
2.
you how many electrons can L have maximum?
2 times 2 is 4, 4 times 2 is 8.
Square.
Oh, so 2 times 2 times 2.
Square.
2 squared is
4.
4 times 2 is 8.
Is this is also the formula for the pixels?
So 2n.
2n is a bit.
So the n is 2.
There's
So
2 and 2
2 to the power of n.
Oh, 2
So all
times
that
2
comes
squared.
first, follow the order of operation.
Right, Miss May? 2 to the power of
2 squared.
Multiply,
Give me a
divide,
marker.
right, add it
Divide.
together.
Because L is in the center.
Yeah.
You almost lost all extra credit for the rest of the.
So K, L, M, N. I'm gonna ask you how many electrons can L have?
Can 2m.
Yeah, 2 to the 2 square is 4.
So K2.
So N, L,
Oh,
right?
L.
Yeah,
So
that's
it's
what I was
2.
saying, like 2. Yeah,
Two square
gotcha.
is 4 times
2 square is 4.
and 4 to
2 times 4 is 8. So L can have a total of 8.
So we have to know that.
Yes.
So if it
I just
is
know what I know.
M, it'll be 3 times 3 times 2.
Mhm.
3 squared times 2.
Mhm.
So 9 times
So it'd be 18.
order of operation.
Yes.
It's always on.
So you see how here, this is M. What was the number you said, Nancy? 18? 18? But it can have less than 18 also, but never more than the maximum.
More than 18. So the max is 18.
Potassium.
The shell, 1, 2, 3, 4. The shell number is N.
You could refer to the formula later.
I'll write that down.
So each shell has its own limit on the number of electrons it can hold. Based on the formula 2n squared, that should be a subscript or superscript, when n is the shell number, right? My formula right there. Does everyone understand that, by the way?
Mhm.
Okay. So the innermost shell K can only hold 2 electrons. Why does that say 12?
It's 1 squared.
Yeah, it should be 1 squared. So the outermost shell is called the valence shell. Yes, you have to know that for the test.
Valence electron.
And the outermost shell has a different rule than the 2n squared. It's called the octet rule. Meaning it does not matter what number you give me in the shell. It is in fact the outermost shell of the maximum that it can hold is 8. That's called the octet rule. So if you take a look at this picture here, n is the outermost shell, it only has 8. It can never have more than 8.
You can have less than.
It can have less than 8, yes. Can I move on? So we're gonna move into some definitions now. The atomic number, or the Z number, which most likely you'll find here at the bottom, that's going to represent the number of protons in the nucleus of the atom. And if otherwise stated, just assume that the atom is stable, which means it's going to have the same number of protons and the same number of electrons. So if I give you something like this with a number, that's going to be our atomic number, right? Which represents the number of protons. So for example, if it's 12, you can tell me, yes, this atom has 12 protons and also 12 electrons. Because if I don't tell you that it's unstable, just always assume that it's stable, meaning it has no net charge. If something doesn't have a net charge, that means the number of protons and electrons are equal. And this number up here is going to represent our mass, which is protons and neutrons. Mhm.
A is the number.
Yes. And then last we have our chemical symbol, which is going to be the abbreviation of the element. For example, H would be for hydrogen. O would be for oxygen.
So you always have the same number of protons and electrons, correct?
Mm-hmm.
I just wanted to say that.
Yes. Because atoms or elements are always trying to be stable, so just always assume that it has the same number of protons and electrons.
And mass, 12 is the number of protons and electrons, atomic number. 6 is.
We'll do an example in just a second. So what is another name for the particles in the nucleus of an atom?
Nucleons.
Nucleons. And if I ask you, name some of the nucleons that you find in
Protons and
nucleus.
neutrons.
Ready? If I finish today, I'll send y'all this part.
When is exam 1 again?
What was the answers for
Next Friday?
Did it tell you about the number of electrons?
I'll tell you in just a second, Jones.
She said next Friday.
Next Friday.
Next Wednesday.
Is it Wednesday?
I don't know off the top of my head. So if you take a look at the atomic number, you should automatically know that's a number of protons. And if it's a stable atom, that's also the number of electrons.
Yeah, next
Yes.
Wednesday.
So now, since we're talking about stable atoms, are we gonna go into ionized atoms?
Just a little bit. So, for example, we have carbon here. So the number at the bottom, what is it?
Atomic.
atomic number 6, which represents the number of protons that we have, and also the number of electrons. The number up here, 12, is going to be our mass, which is the number of protons and neutrons. So, atomic number is 6, that means the number of, oh, there. 12 minus 6 gives you 6. And then atomic mass is our number of protons and neutrons in an atom, and we already know that it's 12. So if I didn't give you this 12, how would you calculate the mass number?
Add protons and neutrons.
6 into 2.
Yes. And if I didn't give you this number, 12 minus 6. So this number will always be the protons and electrons, and this is going to be the sum of protons and neutrons.
So the smaller number is the yeah. So
So they're equal.
Say that again?
So if you give just 12,
Mm-hmm.
which is protons and neutrons, or yeah, protons and neutrons, you're saying 6 neutrons and 6 protons?
Yes. Because we know that the 12 is our mass number, and our mass is calculated by adding up protons and neutrons. Mhm.
But if you don't give that, how do you find it?
Is it always divisible by 2? I think that's what she's asking.
Yeah.
Are the protons and neutrons equal? Is it all the same?
Unless I tell you, just assume that it is. Okay, so now we are going to learn about different ways to classify atoms and elements. So there's 4 different ways: isotopes, isotones, isobars, and isomers.
oh Lord.
They're really gonna ask questions as if I'm an registry.
The group told me that there was only PRE and everything.
There's gonna be PRE, there's gonna be rad bio, a lot of rad bio, some positioning, some labeling.
She said she only had one issue.
So, isotope atoms, what does that mean? So, the P in isotope is going to be an easy way to remember that they have the same number of protons, meaning the same atomic number, but different number of neutrons.
Oh. Like, oh man, it's not okay.
It's an abnormal atom.
So these are 3 isotopes of hydrogen. Isotope P, they all have the same number of protons. So they all have just 1. But you see that they have different neutrons, right?
One has 0, one has 1, one has 2. What do you mean by 1 H and 2 H and 3 H? Hydrogen, the first one hydrogen atom, second hydrogen atom.
Yeah.
Protium, deuterium, tritium.
Don't worry about those words. I just found that image to show you an example. Alright, so those are isotopes. Isotones has the N. So what do you think what do you think?
Neutrons.
Same number of neutrons, but different number of protons. So if something has a different number of protons, that means their atomic number is not going to be the same.
Wait, repeat that again?
So isotones, N, they have the same number of neutrons, right? but their number of protons will be different. And we know that the atomic number represents what?
Neutron plus
The number of neutrons or the number of electrons. So these two different atoms, if they're isotones, their atomic mass number, or atomic number, sorry, will be different. Y'all are so lost.
Yeah.
Any number of
Why is it
neutrons
compared
in
to the
atomic
electrons
numbers also
then?
protons?
Is it that the neutrons and
Okay,
protons are equal?
listen, focus.
Neutrons and
Water isotones, they have what? Same number of neutrons, but protons are different.
Mhm.
So if two atoms have different number of protons, do they have the same atomic number?
No.
No, because we know that the atomic number on the
Is the
bottom
num-
represents the
number
number of
of
protons
protons.
that an atom has. But isotopes have the same number of protons, so they both have the same atomic number.
So isotones have different atomic numbers.
Yes.
With different protons.
So isotope has the same atomic number.
Yes, because they have the same number of protons.
Oh, I'm looking at the wrong one, got it.
So if something has the same number of protons, they're gonna have the same atomic number.
Atomic number is the number of protons.
Yes. If something has different number of protons, their atomic numbers are not gonna be the same.
This is as simple as that.
It's as simple as that.
Yeah, yeah,
It's just
your word gonna
remembering.
come back and hunt you.
So, so
You know
next
what
class,
you're
I'm gonna
doing.
quiz you, you should be able to answer, right, Shaheen?
I suppose so. Then.
Right, that's what I said, her word gonna come back, get up.
Now we're gonna get into isobars. What do you think that is?
A bar.
A bar.
Happy hour?
So look at the A.
Atomic something.
So they have the same atomic mass number. What does the atomic mass number represent?
Protons and neutrons.
Protons and neutrons.
Atomic number is different from atomic mass number.
Yes. Because we know, how do we calculate an atom's mass? By adding up
Protons
protons
and
and
neutrons.
neutrons. So if two atoms are called isobars, we know both of them have the same mass.
Yes, ma'am.
Protons and neutrons. So they have the same atomic mass, but what do they have different?
Atomic number.
Yes.
The total is same then.
Yes.
One is more.
Correct.
It's confusing for no reason.
Why would the atomic number be different?
Protons are
So
the neutrons.
they have a different number of protons and neutrons each. So like if one atom has a mass of 12 and the second one has also a mass of 12, they're isobars, right? But out of that 12, one atom could have 7 protons, the next atom could have 4. That's why they're different. So they have a different number of protons and neutrons each.
That make up the same total mass.
12, correct. Last one. Isomer, we have an E. So they have the same atomic mass number. The last one had the same atomic number, this one has the same atomic mass number.
It has an end.
Wait, the last one had the same atomic mass.
Let me go back.
Same atomic mass. Yeah, it's on.
Oh, sorry guys. So isomers have the same atomic number and same atomic mass. So this one has two things that are same, atomic mass and atomic number.
On the same number.
Why is the energy level different now?
I'll go over that in just a second. So, two isomer atoms, if I ask you what's special about them, you're gonna tell me they both will have the same atomic number and they both will have the same atomic mass. But where they differ is that the amount of energy that they have in the nucleus. So one would have a different nuclear binding energy than the second one. That's where they have the difference.
So that's possible. Neutrons and protons can have different binding.
Not neutrons and protons, we're talking about the nucleus. The energy in the nucleus of these atoms are different.
So different atoms from different elements can be isotopes of each other. Isotones being different
Number.
atomic numbers but same neutrons.
So two atoms could be isotopes, isotones, isobars, or isomers.
We saw 20 minutes. This class is very long.
This class is very long.
Mm-hmm.
Oh, I'm sorry.
Okay,
What
I
time
guess
is it?
it's because I'm used to patient care.
Those days are gone, man. Not fast.
How long is patient care?
It's
30
the
minutes
energy
sometime.
level of the inside.
So the picture over here shows two atoms that are isomers. One, let's say the parent atom, that is in the excited nuclear state because it has a higher energy. And that would be represented with a little M next to it, which stands for metastable, meaning like highly excited. And this one,
I think it's excited. The name has stable in it, but it's highly excited.
highly excited state, because it's the energy in the nucleus is very high. This one, on the other hand, the energy level is different. That's not as excited as the parent. It does not have an M next to the chemical symbol. That's all you need to know. Don't overthink it. See if the second one is stable. The second one is stable. The first one is in an excited nuclear state.
The next one is, sorry, ma'am?
So this one right here
Yes,
is
ma'am.
stable. This one is in an very excited nuclear state. That one is called metastable. It's not stable. It's very, very excited due to the high energy in the nucleus.
You said the daughter one was just stable, regular stable.
Yes. I won't ask you questions like this, but I will ask you what's different in the isomer. They have different amounts of energy in the nucleus.
Can you go to the second slide for isobar? There were two of them, right?
I think there was only one.
Which is the one that said metastable?
Oh, this one.
Oh, isomer. That was the last one.
Should I keep going or? Yes. 7. Or 8, sorry.
Yeah, so you can tell that everything's done.
Okay, so this is just a summary of what we just went over. Isotope,
So much easier.
I mean,
Beautiful.
I still gotta explain it. Should've led with that. No, I'm kidding. I even color coded it for you guys.
You know what? I got $6 for you.
Everybody else get 10 and 12. You need to give her $20.
It varies on how my money is on that day.
Give her a little Oh yeah.
Yeah, give her
Put a
like
mark.
more marks.
You're
Yes.
invited to the next pizza party.
Top tier.
Yeah.
No, you definitely
I'm
invited to the
invited to the
barbecue.
barbecue.
Yeah, I was gonna say that. Come on, Shamika.
Well, she been at
The-
the barbecue.
no. The cookout.
Like,
The
Come on.
No,
cookout.
I'm invited to the continent side.
Ah,
Yes.
Like since we are ending in
And
May,
you
are we
get a
having
couple
a,
shots.
are we having a barbecue?
It's gonna be
You
May.
get a couple
Next.
shots. Yeah.
Oh, y'all got that?
That was a good
Oh,
one.
y'all got that?
All right, so let's see if you guys understood anything. Classify the following elements.
I need some labels. What was the
Number 1. So you notice that there's 2 6s on the bottom there. What do those numbers represent?
Atomic number.
Atomic number, meaning
Number of protons in the nucleus.
yes, same number of protons. So what are they? Isotopes. Okay. Number 2.
They're isotone.
So do some calculations here. The
Isotones.
The neutrons are
can you
different.
explain why, Charles?
Because they have a different number of protons.
Different number of neutrons.
They have different number of everything. I know, but whenever you subtract them, they both equal 7.
So,
they're
What's 13 minus 6?
7.
7, okay. And 14 minus 7?
7.
So what do they have in common?
They're mass.
Yes. No, wait, not mass. The number of neutrons.
Atomic number?
Neutrons are-
Atomic number? So they're isotones.
Mm-hmm. So, can someone explain the logic behind why they chose isotones? 13 represents what?
Atomic
Atomic mass, right? And what is atomic mass?
Rate
Protons.
of proton and neutrons together.
Yes. Okay. So
Charlie,
the
we love you.
total number of protons and neutrons is 13.
Yes,
Why you sit all the way back there?
Here, the total number of protons and neutrons is 14. So now we need to figure out how much neutrons does this one have. And how
6.
can we do that?
Because the atomic number is the
13
number for
minus 6.
Yeah,
Yeah.
that's 7.
Right?
That's all I know.
Total minus the number of protons will give you neutrons.
Yes.
Total minus the number of protons will give you neutrons. I feel like some people are lost.
Did you have that written on the slide?
Yeah, I don't.
I remember seeing.
I'm explaining it now.
I'm a visual learner.
Do I need to write it on the board?
Yes.
Yes,
13, 6, C, and then.
Okay.
So 6 is the atomic,
Atomic number. It's on the bottom.
13 is the
Atomic mass number.
okay. So the atomic number represents what?
Number of protons.
So we have 6 protons. And here we have
7 protons.
7 protons. And we have 13 total mass, which means
7 neutrons.
that's the number of protons and neutrons. This is the number of protons and neutrons. So they're giving you how many protons are in the atom. All we need to figure out is how many neutrons there are. So how will we do that?
Just subtract.
We're just going to subtract it. 13 minus 6.
7.
And then 14 minus 7.
Oh, I don't know that one.
So both of them have the same neutrons, so they are isotones.
I like the way you told us scan for neutrons. That's probably the very key thing to remember.
Did everyone understand?
Thank you.
Isotope?
So, number 3, what do you think that is? They both have 14 here at the top, which is the same atomic number. Same atomic mass, which means protons and neutrons are the same, and therefore they are
Isobars?
isobars.
What do you
Isobars
mean
have
protons and
I know.
neutrons? Ma'am, what do you mean protons and neutrons are the same?
Cause that's the atomic mass.
But that doesn't say that. It
That
isn't.
board said
If
it.
you're seven,
The atomic mass
So
is the
this is
top.
the atomic mass, correct?
Right.
Jackie? 14 and 14. What thing or what's a term to describe something that has the same atomic mass?
neutron,
Who is that?
No, no, no,
protons,
no, no, no. It starts with an I.
oh, I, that I'm not so sure, but I'm not sure.
They all start with
Isobar. So isobars have the same atomic mass. Okay? I'm gonna come with the worksheet next time.
Yeah. And then, is that the same, what is the number of atomic number and proton there?
Actually, do.
No, I'm asking you, these two atoms are called or classified as what? Isobars, because they have the same atomic
Number.
mass,
That's what
not
I'm-
number.
Mass.
It's on the bottom.
Yes, ma'am.
Mass is on top, numbers on the bottom,
Right.
okay? MN. What about, number 4? How will we classify those?
Atomic mass is different.
Atomic mass is different, so they're not isobars. Protons are different, so they're not isotopes. What about neutrons?
Neutrons are, oh, neutrons are
Neutrons
the
are
same.
same, which means what? Isotones.
Oh.
See how we did that? Number 5, we noticed that they have 99 at the top, same atomic mass. And then they also have 43 at the bottom, same atomic number. So they're what?
Isomers.
Isomers.
What is the M format?
Oh, everything.
Metastable.
Metastable.
Now what is that?
Don't worry about that. I just want you to focus on the numbers. Yes.
Are isomers always gonna have at least one saying metastable?
Yes.
Okay, so can we focus on that then?
Isomer isn't a thing.
It won't be on the test, if that's what you're saying.
Yeah.
Sorry, fine.
Because if we're going by the whole letter thing for, like, remember you said isotopes have the same number of protons, like P. Isomer is the only one with an M.
Oh, so the M in the metastable does not have to do with isomers,
Oh,
or
okay.
remembering isomers, if that's what you're saying.
That's what I was asking.
Yeah, so isomers will always have the same atomic mass and the same atomic number.
Just different energy levels.
Yeah, just different energy levels. So if you see a small m, that means one is in an excited state and one is not, meaning different energy levels. So they're isomers. Last one,
Atomic number is same, atomic mass is different, so neutrons are different. The
atomic
number
number is the same, which means what?
of protons are the same.
Protons are the same, which means what are they classified as? Isotopes. Got it, Cody?
Yeah.
Janelle, you good?
Cody's been got it.
Janelle's so quiet.
Basically ask something.
I don't know y'all.
What was the last one?
Isotope.
She's like,
I'll give y'all a
Isotone?
worksheet.
Please.
Tope?
Because
With the P.
protons are.
Just say with the P or N. With the P. Thank you.
There's 53 is protons.
I'm hungry.
Hi, Hungry. Nice to meet you.
Yeah.
I think I'll stop there for today.
Do we
Because
have
I want
more?
you to marinate in this.
Can we still get the PowerPoint?
Yes, I will send you the PowerPoint. I just have 6 slides, which I'll
And
finish.
you have a
Good.
picture with what's in the name answers.
The answers? No, I don't. So they have different number of protons. So what can we eliminate? Isotopes, because they don't have the same number of protons, okay? What else can we eliminate? Isomers, because none of their atomic mass or numbers match, so we can eliminate that. So we're left with 2 options, which is what? Isobar or isotones. Would it be an isobar?
No,
No, because why?
they have different atomic numbers.
Atomic mass.
They have different atomic mass. So then what would be our last option? Isotones. And just to be sure that they are in fact isotones, we can
Minus and C.
take our total neutrons and protons and subtract it from the number of protons. 13 minus 6, which is 7 neutrons. And then 14 minus 7, which is also 7 neutrons. So therefore, we know it is in fact isotone.
Okay.
Got it?
Yeah.
Number 3, Samantha.
Let's see, that is. Is it
So what do you notice is similar?
the atomic mass?
Mm-hmm.
Mm-hmm. Similar. It is.
So what term has the same atomic mass?
Is it isobar?
Isobar, that's
Okay.
correct. Number 4.
And you just stop there? Is that how it works?
Yeah,
Same number.
same atomic mass, isobar.
Isobar.
Oh.
Same atomic mass. Isobar.
Okay.
Number 4, Reagan.
Nothing is the same. So
Well, that
You
shit
can
is
Sorry about that.
automatically eliminate a lot of things, right?
isomer.
Isomer, how did you reach that conclusion?
I just remember isomer was everything, so everything's different.
Mm,
Everything's
no.
same.
Or same. Wait, what? Everything is the same.
Isomer, everything is the same.
Oh, okay, wait. Then I don't know.
For number 4?
So for number 4, they don't have the same atomic mass, so they're not isobars. They don't have the same atomic number or protons, so they're not isotopes. And
So-
they're not isomers. So what's left?
Isotone?
Isotones. And how can we check to make sure that it's right?
Subtract, but I couldn't do that in my head.
Someone want to help around?
I'm gonna post it.
132 minus 54,
12 minus 4 is
78.
17.
and then 131 minus 53.
79.
Okay, so the same number.
131, 17.
So they have the same number of
Okay.
neutrons. Number 5, Angelica.
Wait, isn't that a isomer because they have it?
Yes. Same thing, same. Isomer. So if I give you a pair of isomers, one is always going to be metastable, because remember, the difference between them is one is always going to be in a higher energy state. And then last one, number 6,
So iso, with the P.
53 and 53, same
Protons.
atomic number.
Oh.
So protons, isotopes.
So is this right? So going down, it's isotope, isotone, isobar, isotone, isomer, isotope.
Sure.
Sweet.
Yes,
For number 5, which would be the metastable one? The first one?
with a little m.
Oh, okay, I see.
Lord, we need
And
you.
that concludes our presentation for today.
Do we have a physics chat yet?